Welcome back. I will now ask you some questions about statistics. So, my first question about the statistics is say you are running a multiple linear regression and believe that there are several predictors that are correlated. How will the results of the regression be affected if they are indeed correlated? How would you deal with this problem? Thank you for the question. Now, there are two main problems here. The first is that the coefficient estimates and size will vary dramatically depending on what particular variables you included in the model. In particular, certain coefficients may even have confidence intervals that include zero, meaning that it is very difficult to tell whether an increase in that x value is associated with an increase or decrease in the y value. The second is that the resulting p values will be misleading. An important variable might have a high p value and deem insignificant even though it is actually important. We can deal with this problem by either removing or combining the correlated predictors. In removing the predictors, it is best to understand the causes of the correlation. For example, did we include extraneous predictors or such as both x and 2x in our predictors? For combining predictors, it is very possible to include interaction terms, for example, the product of the two. Lastly, we should also include the center data and try to obtain a larger sample size, which will lead to narrower confidence intervals. Thank you for the answer. Now I will ask you the next question on about statistics. Can you derive the mean and variance of the uniform distribution U A comma B? Thank you very much. So I will denote the capital X as the variable, statistical variable from the distribution of U, uniform distribution of U A comma B. And now I will have the following probability density. Fx equal to 1 divided by b minus a, since it is a uniform distribution. Now I can calculate the mean as the integral of um, the probability uh, density times x and integrate it from a to b. So after integration, I will guess the expected value of the mean as a plus b divided by 2, which is a very sensible outcome. For the variance, I will have the formula of variance of x is equal to the expected value of x squared minus the expected value of x squared. Now I will have the expected value of x squared equals to the x squared times the probability density and integrate it. And at the end, I will have it as a squared plus a times b plus b squared divided by 3. Therefore, the variance of x is equals to a squared plus b plus b squared divided by 3 minus the square of a plus b divided by 2. And at the end, we will get it as b minus a squared divided by 12. Thank you for the answer. Now I will ask you my next question regarding statistics. Imagine that you are drawing from a normally distributed random variables x with normal distribution of n parentheses a comma 1 once a day. What is the approximate expected number of days until you get a value of more than 2? To repeat, imagine that you are drawing from a normally distributed standard random variable, which is normalized um, and with zero mean and one variance once a day. What is the approximate expected number of days until you get a value of more than 2? Thank you for the question. So, because you mentioned that x is normally distributed, we can look at the CDF function of the normal distribution. To check the probability of x being at least 2, we can we can check it as the probability of x smaller than 2, which is equal to the probability of x smaller than the mean plus 2 variance of mean plus 2 standard deviation, which is equal to 0.977. Now we have probability of x greater than 2 being 1 minus 0.977, which is equal to 0.023 for any given day. So for any given day, you have the probability of getting anything larger than 2 for 0.023 on probability only. Now, since the draws are independent of each other each day, the expected time until drawing x greater than 2 follows a geometric distribution with p equals to 0.023. Now let t be a random variable denoting the number of days. Then we have the expected number of days equals to 1 over p, which is equal to 1 over 0.024, approximately 43 days. Thank you for the question. Thank you for the answer. Now, now I will ask you another statistics question. So you have a coin, and you flip it 1,000 times. Among those 1,000 times, you have 550 times that it show up as heads. Do you think the coin is biased? Why or why not? Thank you for the question. So to determine whether the coin is biased, and you asked from what you asked, the sample size of flips is also relatively large. So you have 1,000 flips, and now we can apply the central limit theorem. Because each individual flip is a Bernoulli random variable, we can assume it has a probability of showing up head as p. Then we want to test whether p is zero point 0.5, whether it is fair. The central limit theorem allows us to approximate the total number of heads seen as being normally distributed. More specifically, the number of heads seen should follow a binomial distribution since it is a sum of Bernoulli random variables. If the coin is not biased, so that which means p equal to 0.5, then we have the following on the expected number of heads. The expected number of heads is simply equal to n times p, which is 1,000 times 0.5, which is 500. And the variance is given by np times 1 minus p, which is equals to 1,000 times 0.5 times 0.5, and this is equal to 250. And the standard deviation is square root of it, which is approximately 16. Because the mean and standard deviation specifies the normal distribution, we can calculate the following z-score for 550 heads. And the z-score is 550 minus 500 divided by 16, which is greater than 3. With z-score greater than 3, It means that if the coin were fair, for events of seeing 550 heads should occur with less than 1% chance under normalization or normal distribution assumptions. Therefore, we can conclude that the coin is likely biased. Thank you for the answer. I will have my next question, actually my final question on probability to you. Given that a random Bernoulli trial generator, you have a Bernoulli variable and a generator of it, how do you return a value sampled from a normal distribution? To repeat, given that you have a random Bernoulli trial generator, how do you return a value sample from a normal distribution? And that is the last question for you. Thank you for the question. Since I have the Bernoulli trial generator, I can generate n Bernoulli trials, each with a success probability of p. So I have a random variable x1 up to xn, and they are Bernoulli distributed with probability p. Assuming they are IID, independent random variables, we can compute the sample mean for p from a large number of trials, which is equal to the number of summation of xi divided by n, and we know the expected value of this sample mean is np divided by n, which is exactly equal to p. Additionally, we can also compute the variance of this sample mean, which is np times 1 minus p divided by n squared, and it will get us to p times 1 minus p divided by n. Because we assume that we sample from a large n, and due to central limit theorem, our sample mean will be normally distributed, and the normal distribution have n parentheses p, comma p times 1 minus p divided by n, close parentheses. Therefore, we can take the z-score of our sample mean as the mean minus p divided by the square root of p times 1 minus p divided by n. And this z-score will then be the simulated value from a standard normal distribution. All right, thank you very much for attending this interview. I have completed my I will complete the interview by thanking you again. So to recap, your performance on the probability interviews and also the statistics interviews are impressive, and we will review the answers again after looking at the recording and after looking at our Zoom meetings. But I can tell you that your performance is really good, and we want to move on the next step, and we will interview you in approximately 2 weeks. Thank you very much and have a good day.